Hello, everybody. I want to talk to you a little bit about electric fields today. And electric fields are a somewhat complicated topic that people sometimes struggle with, so we're going to go into a little more depth here. The big questions for electric fields are, does one charge create anything? What's a test charge? And how do we define the electric force in a more general way than Coulomb's force? So the first question is, does one charge create anything? Well, does one charge have an electric force that acts on it? No. Newton's third law says it takes two to tango, basically. And I have to have two charges present, one to act on the other, and the other to create the equal but opposite reaction. So, where have we encountered something like this before? Let's think about the law of universal gravitation. Well, the law of universal gravitation, we had two objects in place, not just one, right? And when I thought about, say, me and the Earth, I said, okay, well, I have G that's a constant. When I'm thinking about a person on the Earth and the Earth, well, the Earth's mass is constant. And when I'm near the surface of the Earth's radius is what really dominates that height. So I can take this whole big term right here, and I can just call it G, which we said was 9.8 meters per second squared. Well, G can also be thought of as the gravitational field strength of the Earth, and in that case, G, maybe I'll give it a vector in this case, would also be 9.8 meters per second squared, but for any object would be G mass of the body divided by R squared. And then I could say that the weight of an object on this body would just be the gravitational field strength times m, so m times the gravitational field strength. And this gravitational field strength is what's created by a single mass. We can take that same idea and apply it to an electric field. So if I have a single charge in a vacuum, I can say it produces an electric field equal to kq over r squared if it's a point charge. And that means that it will produce a force equal to the electric field times a charge when another charge is placed nearby. And we usually draw lines for this. When I talk about masses, I don't have to worry about attractive or repulsive, but when I talk about electric fields, I do. So I have a few rules for electric field lines, and one is that arrows always go out of positive charges and into negative charges. And that's because we're going to say that it's the force that would be produced on a test charge when it's placed nearby, and the test charge is always positive. So if I put a positive particle by a positive particle, it's going to be pushed away. The other rule is that electric field lines are, the number of lines coming out are proportional to the strength of the field. So if my charge here is 2q, I might have eight lines going out. And if my charge here is q, I would only have 4 coming in. So that gives me an idea of the relative field strength. And the last rule is sort of the further the lines get apart, the weaker the field is. So as if I move away from this positive charge, the lines get further and further apart, so the electric field gets weaker and weaker. Same thing with the negative charge. So this gives us our definition of a electric force that is a little bit more general of a definition than Coulomb's law, and it works for any electric field that's present. It says the electric force on a charged particle is equal to that particle's charge times the value of the electric field at that location. So we can sort of check ourselves a little bit here, and we can say, well, what if I have an electric field that's pointing this way, right? all up. Well, in the positive y direction. If I put a positive charge here, I would see that the motion would be up because the force would be positive QE. And if I put a negative charge in this same field, it would go down because it would be negative QE. So this is an equation that doesn't just give us the magnitude, but also the direction, because I can put the sign of the charge in my force equation, and that gives me the sign of the motion for my electric field. So it goes in the same direction as the electric field if it's positive, and in the opposite direction if it's negative. This is a useful tool because it allows us to find the electric field on a distribution of charges or multiple point charges also, because we have the superposition law, which says that the total electric field is just the sum of each of the individual electric fields. So if I had my example from before, where I had my multiple point charges, so let's say I had one here, and one here, and one here, and I wanted to find the electric field at this location, I could find E1 at that location, E2 at that location, and E3 at that location, and then take the vector sum. And again, I have to be careful here because here I know it will just be EX, where EY will be 0. Here I know I have an EY and EX is 0, and here I have an EX and an EY that I have to all add component Y. So maybe I'll put a little X hat and a Y hat there to remind us that those are unit vectors of the components. And then I would do the component-wise adding, and then use my vector mechanics to solve the rest of the situation. All right. So that's a little introduction to electric fields, and if you have any more questions, feel free to ask them in class, or we could make more videos to go over these ideas. Thank you.